In this video, we're going to take a closer look at exactly what the multiple regression equation is describing and how it works. Now, as we talk about adding predictor variables in order to make better, more accurate predictions in multiple regression, some students start by thinking of the regression line in simple regression with one predictor, and they think that as we add predictors, we just start to make that line bend and twist in ways that gets it closer to all the dots in our scatter diagram. Kind of like
connect the dots, la 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 la, connect the dots, la 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 la.
But it's nothing like that. The real answer is much more elegant and beautiful. To see exactly how it works, let's go back to our adolescent behavior problem example, and we'll take another more accurate look at how the shape of the regression equation changes as we add variables. Now, we'll modify the example slightly so that the data and patterns are more clear visually. Okay? So, in this example, we'll have 25 youth, and we're predicting their scores on a problem behavior scale based on parent and peer emotional support. Let's start with 0 predictors, just our outcome, just looking at behavior problem scores. Now, we can visually represent those scores on a line, a number line, a one-dimensional number line. When all we have are the values for our outcome, one variable, adolescent behavior problems, what would be our best prediction for someone's score? If that's all I know, what's my best prediction for someone's score? Hint? We want the number that will give us the smallest square deviations from whatever that number is. We know what that is. It's the mean. A fundamental characteristic of the mean is that it has the smallest sum of the square deviations. In this case, we can also think of the mean as our y-hat, our predicted score for a model with 0 predictors, right? Because it is what we would predict if we had no other variables in our model. If we knew nothing else, we'll predict the mean. So here in our visualization, we'll show the mean as a red dot on that number line. Now the key point is that with 0 predictors, our data can be represented on a one-dimensional line, and our predicted score for someone's score is the mean is a 0-dimensional point on that line. That 0-dimensional point that minimizes the square deviations around that point, around the mean. Now, while a line worked for illustrating the distribution of one variable, our outcome, it doesn't work when we have 2 variables. So let's add a predictor. In this example, let's add parental support. Now we're going to need to stretch that line into an additional dimension. And we'll make it a 2-dimensional XY plane in which we've added parent support as the x-axis. Notice the y-axis, indicating behavior problems, will remain unchanged. And in fact, the distribution of scores along that y-axis is the same. But now we're going to stretch each of those scores along the new x-axis based on someone's level of parental support. Okay, here we go. Now, let's also move the red point indicating the mean for behavior problems and place it at the mean for both parent support and behavior problems. So we took a one-dimensional line that illustrates the distribution of scores for one variable. We stretched it into a 2-dimensional plane illustrating scores across 2 variables. One variable is our outcome. You can represent it with a one-dimensional line. But with 2 variables, our outcome and a predictor, we need to stretch that line into a two-dimensional plane in order to represent the scores on both of those variables. Now, what about our predicted score? Well, when we had 0 predictors, right, just the outcome, our prediction was the mean for the outcome, a point on a number line for the outcome scores. 0 predictors, a zero-dimensional point for our expected value. But by adding a predictor variable, now we're going to stretch that zero-dimensional point into, you guessed it, a one-dimensional line. Our regression line in simple regression. Pretty cool, isn't it? Now remember, the regression line minimizes the squared deviations around the line. Our prediction, our point on that line, will have the smallest possible total sum of the squared residuals, those squared errors, all along that line. In that way, it's kind of like the mean, but instead of minimizing the squared deviations around a single point, now with the regression line and one predictor, we're minimizing the squared deviations around a line, our regression line. Now, what about when we add a second predictor, peer support? That will give us 3 variables, right? Our outcome, problem behaviors, and 2 predictors, parent support and peer support. With 3 variables, we need to stretch our graph of that data into a third dimension, literally pulling the points off the screen if that were possible. Okay, so here goes. Now, it's a little harder to see, but now we're graphing data in 3 dimensions with an X and Y axis at the bottom that are used to indicate a person's score on both of our predictors, peer support and parent support. And that vertical Z axis indicates someone's level of behavior problems. With 2 predictors, we also need to stretch our regression line into a 2-dimensional plane that indicates someone's predicted outcome based on both of our predictors. It looks something like this. Now, we're still minimizing the squared deviations between our predicted outcome score and the observed outcome scores, right? To see how this works, let's assume that our regression equation is y hat, our predicted score, equals 18.5 minus 2 times peer support minus 1.5 times parent support. We'll keep the numbers nice and round for this illustration. If my peer support score is 2 and my parent support score is 3, what would be my predicted behavior score? Well, we just plug in 2 for peer support and 3 for parent support, plug those into our regression equation, and we get y hat, my predicted score, is 18.5 minus 2 times 2 minus 1.5 times 3, which works out to y hat equals 18.5 minus 4 minus 4.5, or 10. That's my predicted score based on this model. Now visually, our model, that regression equation, is the equation for creating that green plane. Our predicted scores based on peer and parent support are points on this plane, just like in simple regression where our predicted scores based on one predictor were points on a regression line. Now we can visually see that here if we take this apart step by step. All right? Peer support was equal to 2, so we first move along the peer support axis 2 units, and parent support was equal to 3, so we move along the parent support axis 3 units. Solving the regression equation tells us that the value here for the point on that plane based on these two specific values for peer and parent support is 10. That's our y hat. That's our predicted score on the outcome. Do you see the pattern? For each variable in our model, we need to stretch our data into another dimension in order to graph it. And with each additional predictor in our model, we need to stretch our regression surface into another dimension, from a prediction point to a prediction line to a plane, and so on and so on. Now, once you have 3 predictors, it becomes hard to visualize this, right? Our regression prediction plane is stretched along another dimension into a regression cube. With 4 predictors, we have a 4-dimensional hypercube. It can take a little cognitive leap to think in those sorts of higher and higher dimensional terms. Our 3-dimensional brains just can't visualize something like that. Ask Mr. Spock.
Other dimensions, higher levels of being,
the existence of which cannot be proven logically. Therefore, V'ger is incapable of believing in them.
What V'ger needs in order to evolve is a human quality. Our capacity to leap beyond logic.
Yeah, this may require a little bit of a leap, but the underlying math stays the same. Whether we have 2 or 10 predictors, our regression equation is finding the surface that goes through all of those points in however many dimensions we need that will minimize our squared residuals. It's not some game of connect the dots. It's much more elegant than that. This is how multiple regression works. This is what the regression model creates for us. Okay? So let's wrap up our video here. In our next video, we'll take another look at conceptualizing multiple regression that focuses on understanding the variance in our outcome measure using what are called Venn diagrams. Okay? See you then.